Hello, everyone. Welcome to yet again another live chemistry tutoring session on Sunday. That is awesome that we're doing chemistry on a Sunday. That just shows your dedication. Happy to have you guys here. Today, we're going to be going over limiting reactants, excess reactants, empirical, molecular, all of this fun stuff. So before we begin, I just wanted to mention to make sure to save your spot for next Sunday. I haven't decided what I want to cover just yet. I actually wanted to ask you guys, so if you have anything specifically that you want me to, recover, whether it be dimensional analysis or maybe if you completely different, I want to go ahead and give you the chance to let me know. If you can write in the comments or write in the chat, let me know what you would like me to go over possibly next Sunday. I know everyone is, either in so you guys are on different levels or different sections. So it just helps me to know what I need to teach. Okay. Electronic configuration. Okay. Then I will definitely consider that. Anyone else? Is there anything else that you guys wanted me to teach for next Sunday? Let me know in the chat. Anyone's doing anything different, whether it be dimensional analysis, gas laws. I know everyone's doing something different, but at any point, let me know in the chat, whatever you'd like me to cover for next Sunday. Okay, so I'm going to jump right in. We're going to be talking about limiting reactants. It's our first thing right now. Let me focus our screen. And we're going to make a smoothie because that's what you do in chemistry, right? You make food. No, but we're going to make a smoothie and we're going to understand the concept more of limiting reactants. So let's say if our first reactant or ingredient is, we have 40 cups of strawberries. Okay, let's just say that. And next we have 2 cups of milk. That's our other reactant or ingredient. And we want to produce our product, which would have been one smoothie or a smoothie. So just to make a note, we have 40 cups of our strawberries, 2 cups of milk, and we need 1 cup of each ingredient or reactant to be able to produce one smoothie. So our limiting reactant is something that produces the least amount of products. So we can look at it as what's going to run out the fastest and not be able to produce as many smoothies as possible. So as we can probably see, the milk is going to run out, right? There's not enough milk, so we will only be able to produce 2 smoothies. So our limiting reactant, which I'll put here as LR, is going to be the milk. What is left over is then the excess reactant, which in our case will be the strawberries. I'm going to say ER, just saying excess reactant. Okay, so another key term to know is our theoretical yield. So your theoretical yield is however much of your product the limiting reactant produces. So meaning our milk, we said, was our limiting reactant, so that only produced 2 smoothies. The 2 smoothies is then our theoretical yield. So once again, theoretical yield, this is really, really important to know, is whatever our limiting reactant produces. Okay, now that we got the main concept down, let's relate it back to chemistry. Let's start with our first example. So let's say if we were to have this balanced reaction, and if we were to have, if 14.32 grams of nitrogen reacts with 4.21 grams of hydrogen to produce ammonia or NH3. And our first question is asking us to find our limiting reactant. Now, sadly, we can't just look at it like we did with the smoothies and tell. So instead, we need to figure out how many grams of our product we're actually going to produce. So our product in this case is ammonia or NH3. We need to figure out how many grams we're going to produce from each reactant. So I'm going to say that again. So I want you to think of like the smoothie again, okay? Where let's say N2 is the strawberries and H2 is the is the milk. And I don't know how much of each I have. I don't know. Actually, I know how much each I have. I don't know which one is limiting or which one is the excess. Okay. I'm trying to figure out how many smoothies each ingredient or each reactant is going to produce. Okay. So our first step with this, when we're just finding the limiting reactant, we're going to convert the grams of each reactant to the grams of product. This is always the case. For a limiting reactant question, we're going to go from our grams of each reactant, and we're going to find a way using stoichiometry to go to grams of our product. All right, so I'm going to develop a plan and help you guys out so we can figure this out together, how we're going to do this. So I'm going to start with the first reactant that we have, which is N2. So nitrogen, I'm just going to write that here. So we start off, it tells us that we have 14.32 grams of N2. Okay, so that's how much we're starting off with. And I realized I actually wanted to draw out a plan before I begin. Let me do that right off the bat. All right, so I just want to start off with grams of N2. I somehow, some way want to magically to grams of our product. So what's going to allow us to get there is moles. So a lot of times also with stoichiometry, we tend to go from grams to moles, and then we'll do a mole to mole ratio to change our compound altogether. So we're going to go from grams of nitrogen to moles of nitrogen. All right, with me so far, guys. So now I want to change the compound altogether. So that's why we have our balanced equation. We use our balanced equation as a mole to mole ratio, and I'll get further into that, a mole to mole ratio to just change our compound. So I'm now going to get 2 moles of our product or our smoothie, NH3, and get 2 grams of NH3. All right. I'm going to go into more and more detail here. So your key hint right here, whenever we're converting either grams to moles or moles to grams, we use the molar mass. All right. So in this case, we're going to go from grams to moles. So our first conversion factor is going to be our molar mass of N2. Then we're going to continue going to moles of N2 to moles of a completely different compound, making it NH3. So we're going to use a mole to mole ratio. Thank you, Diana. You're so sweet. I love your tutorial. I'm happy to help, guys. And I thank you for the feedback. So our mole to mole ratio. Okay. So, and this is used, by the way, we find this using our balanced equation. Okay. So then now, going from moles to grams, we use molar mass. That's our third conversion factor. So molar mass. This is just a breakdown as to how I'm going to go from grams of N2 or grams of my reactant to grams of product or grams of NH3. All right, continuing on. So starting with our given amount of that N2, and we had 14.32 grams of N2. Looking back at our plan, we said that we're going to be using the molar mass of N2. So right then and there, we're going to put our grams of N2 on the bottom and moles of N2. This is just the molar mass of nitrogen. So remember molar mass. There's so much that we have to do. Remembering molar mass, this is really saying 2 times the mass of one individual nitrogen. So nitrogen's mass, looking at your periodic table, is 14.01. So we'll multiply those two together and you get 28.02 grams per mole. This is what I'm going to be using. So it's 28.02 for the grams portion per every 1 mole. All right, that was just the first part. So this allows us to go from grams to moles of N2. Continuing on. Now I'm going to place the moles on the bottom or across from each other so we can cancel out those moles. All right. And then now I'm going to go to moles of NH3 So this is us using our mole to mole ratio to completely change the compound. And where I'm going to find this is heading back to our balanced equation. So we're going to look at the numbers in front, or also known as coefficients. I'm going to place, if there's nothing there, assume there's a 1. So just highlighting the coefficients, this is what you use for your mole to mole ratio. So if we're going from moles of N2 to moles of NH3, there is 1 mole of N2 for every 2 moles of NH3. And that's exactly what I'm going to place in my mole to mole ratio. All right, and this would have been, let's see, we said 2 moles to 1 mole. All right. And then we'll see that the moles of N2 and the moles of N2 also cancel out. We're now at moles of NH3. All right, so this was our first conversion factor, right? Using that molar mass of N2 as our conversion factor. And then our second conversion factor was that mole to mole ratio. Continuing on, we're still not done. We need to get to grams of NH3. So once again, we need another molar mass since we're converting from moles to grams this time. So we'll figure out the molar mass of NH3. So nitrogen, there's only 1. So really 1 times 14.01, or you could have just done 14.01. And then there are 3 hydrogen times our molar mass of just 1 individual hydrogen, which is 1.01. And add that all up. So this would have given us 14.01 plus this would have been 3.03. Adding those together, and we get 17.04 grams per mole. So we said that we're going to align the moles on the bottom of NH3 so they can cancel, and we're finally going to get our grams of NH3 on top. And that would have been 17.04. Okay, that was our third conversion factor. And then that would have then canceled. Moles and moles cancel. We got our grams of NH3. Multiply straight across. Yeah, let me move this closer. So multiply straight across all of these values and divide by 28.02. Oh, by the way, I missed this. That would have been a 1 mole, by the way. So multiplying all that out, let's see what we get. And N2 produces 17.43 grams of NH3. We're still not done. And I realize I have a question. So Arabella asks, so does grams per mole always cross out with the grams? So Arabella, what happens here is to use grams per mole or molar mass, that's always going to be used as our conversion factor, or a way to basically just cancel out grams to get to moles, or cancel out moles to get to grams. See that? So whenever we're going from grams to moles, or vice versa, moles to grams, you use molar mass to cancel those out. And that's why I strategically placed the grams across from each other so they can cancel, and the moles would have been on top. However, you'll notice at the end here, it was opposite. The moles were across from each other so they can cancel because we were looking for the grams. Does that answer your question, Arabella? Let me know. And we're gonna keep practicing. Oh, okay, perfect, great. So that was you're welcome. So that was our first one. We're still not done. We have to figure out what the next reactant is. So we're still gonna use the same amount, like the same setup basically. And I'm gonna go back to show you guys what we're doing. So we're still going to be using that grams of reactant going to grams of product, but now we have another reactant. So we have to now figure out what our H2 would have been, because that's our second reactant. So we're going to go from grams of H2, so grams of H2, then to grams of NH3, somehow, some way. And I'm going to set this up again. So it's basically going to be the exact same setup, just with the different reactant. So this doesn't really change our plan. The only difference here is that I'm starting off with grams of H2, going to moles of H2, and we're going still from moles of NH3 and grams to NH3, but we're using our molar mass for H2. So that's our overall setup, same sort of concept. I'm just gonna do that over here. Give me a second. That would have been 4.21. All right, so doing that now with hydrogen. I'm going to start with that 4.21 grams of H2. And we wanted to get to our moles of H2. So we'll use the grams or molar mass of H2, going to moles of H2. Looking at your molar mass for hydrogen, there are 2 hydrogen overall. So we're going to multiply 2 times 1.01, which would have given us 2.02 grams of hydrogen, or H2, per every 1 mole. Not done yet. So our grams of H2 cancel, and now we're at moles of H2. So this is where we're going to go from moles of H2 to moles of NH3. So whenever you want to change your compound, hint, hint, you're going to use moles of multimole ratio using your balanced equation, all right? So now I want to align the moles across from each other. So that would have been moles of H2, and we're going to moles of NH3. So we're going to go back to the balanced equation. Let's scroll back up to the balanced equation. And now we'll see there are 3 moles of H2 per every 2 moles of NH3. All right, so 3 moles of H2 for every 2 moles of NH3. Scrolling back up. All right, still not done. So we said 3 moles of H2 per every 2 moles of NH3. Cancel what we can. Our moles and moles of H2 cancel. Now we are at moles of NH3. I know these processes are so long. Now we're going to get to our final step, which is going to be going from moles to grams. What do we use? Molar mass. So luckily we really calculated the molar mass of ammonia, or NH3. So that's what we're going to use here. Aligning our moles of NH3 across from each other so they can cancel. And our grams on top, because that's what we want. And then now grams of NH3 will allow us to finally get how much of that mass there is. So let's see, we found that this was 17.04 grams previously per every 1 mole. We'll multiply straight across because, by the way, these moles cancel, and we're at grams of NH3, which is what we wanted. So multiplying these numbers all straight across and divided by 2.02 times 3, let's see what that gives us. That gives us that H2 produces 23.91 grams of NH3. All right, so these are the numbers that I'm going to compare. And I'm going to answer a question here. Okay, I hope I don't butcher your name. So Ebony Brothers? I get why we do I get why we do the conversions, but I don't understand how we get to the point of having to do conversions. Okay. Let me see if I can answer that question for you. So your question is, how did I know how to like instantly go to like grams of reactant and then go somehow to grams of product? Yes, is that what you're asking? Is that, I hope I'm understanding your question. Yes, okay, cool. So how I knew to just automatically do that, and let me actually go back to the smoothie reference. So I know that this one was like so much easier to just spot, right? You can just tell that the milk is going to run out. In chemistry, unfortunately, we can't do that. We can't just instantly spot what's going to run out. So we need to see how everything is actually going to react and mix together. So that's why going from grams of your reactant, then grams to your product is necessary using that stoichiometry or using those conversions, just because in chemistry, sadly, it's just too complicated to be able to actually see what's going on. So does that kind of make sense? If not, I can explain it differently. That makes sense. Let me know. If not, I can keep going with that. I think we can keep just running with it. But kind of want you to just think that, yeah, I think so. Okay. We'll keep going with these questions, but overall, I just kind of want you to know the steps that we have to go from grams of reactant to grams of product, because think of it as we have this amount of reactant or our ingredient, right? And we want to see how much of our smoothies or how much we're going to produce overall. Yet it's not so black and white where we can just instantly see how much we're going to produce, because we have all those chemicals mixing and things, reacting. We have to then see mathematically how much exactly we're going to have. Does that make more sense? Let me know. Yes, cool. All right. So going back to this question for limiting reactant. So we said that limiting reactants will produce the least amount of products because they're limited, right? They get used up completely, or actually completely, and they run out. So the limiting reactant produces the least amount of product. So I'm going to go back to these numbers that we found. And we said that our reactant of nitrogen produced this amount of product, 17.43 grams of NH3. However, hydrogen, H2, our the reactant, produced 23.91 grams of NH3. Which one produced the least? The nitrogen, right? So this one is our limiting. Our limiting reactant is N2. Now, maybe some of you might be asking me, listen, Maribel, do I have to do this every single time? And yes, I'm sorry guys, but it is. This is something that we have to do every single time to figure out your limiting reactant. I wish it was quicker. I wish I had a shortcut, a trick up my sleeve, but sadly, this one, there's no way around it. All right, so now that we found our limiting reactant, which is N2, or nitrogen, I'm going to keep going with the next question. And I'm going to erase a bunch of this because I'm running out of room. But any questions so far as to, yes, I just got a question. All right, so Megan asks, is there some sort of map or guide that you can show us? I don't fully understand how you knew how to go from grams to moles, back to grams. Yes, that does make sense. Let me go back to that, guys, and let me emphasize a lot of these points all over again. Give me a second to erase all this madness. But yeah, that completely makes sense, Megan. I know that it's not easy to just instantly know where to even begin with some of these questions. Let me go back into this. So something to mention, guys, what you're always going to be seeing here is you're always going to be, whenever you're looking for your limiting reactant, you're typically going to be going from grams of reactant to grams of product. So ingrain that in your reactant to grams of product. Okay. Now, if let's say if we were to take this example again, and I'm gonna just redo it. How about that? I'm gonna redo it and have us go back to all this. All right, so I'm gonna start from scratch, and I'm gonna just do gram. I'll do N2 again. Why not? So if we had grams of N2, which is our first reactant, and we're trying to get to grams of our product, which is NH3. Okay, so sadly, we can't just magically get from grams of, N2 to grams of NH3, which are completely different compounds, right? There's no way. We have to do something in between. So in our case, how I knew instantly, by the way, to get to a mole to mole ratio is, that's my tip to you actually, is whenever we're going from moles of, I'm going to say compound A, or really just one compound, okay, or one element, to a completely different compound, you have to use, I'm going to say compound B, you have to use a mole to mole ratio. So that's how I instantly knew I had to do a mole to mole ratio, because these are completely different compounds. Right, that right there, like that's how I knew. So since I was going from grams of N2 to grams of something completely different, NH3, boom, convert to moles. All right, does that help, guys? So I'm going to keep going with that. Okay, so now that I know I have to convert to moles because they're completely different compounds, I'm going to start with that given, which was grams of N2. That's just what they told us. That's what they gave us. So that's where I knew to convert to moles. All right, moles of N2, because I had to change the compound. So now that I have moles of N2, that's when I knew, okay, mole to mole ratio is what allows you to change the compound altogether. So then that's how I got that moles of NH3. All right. And then now, still not done, we had to go back to grams, because that's what we're looking for. We're looking for the amount of mass of product, or how much we're producing overall. So that's how I need to go back down to grams of NH3. Start with your given, grams of N2, right? We're going to change our compound altogether. So that's where this moles came in of N2. We have to change our compound altogether. So we're going to do a mole to mole ratio. That's how I need it. Then I can do moles of NH3. After that, still not done. We needed the grams of our product. So that's how I knew to get to grams of our product, or NH3. And I'll do that little roadmap again. So this first part I said was going from grams to moles. Using anytime you're going from grams to moles, we use the molar mass. And now, here, let me give you an even better explanation why we use the molar mass, by the way. Remember, molar mass's units specifically are grams per mole. So right then and there, it's right there in the units, right? It allows us to get from grams to moles, or vice versa, from moles to grams. Okay, so that's how I instantly always know how to use molar mass whenever I see grams to moles or moles to grams. And then, so that would have been our first conversion factor. And this would have been the molar mass specifically of N2. So the molar mass of our reactant. Then now, moving on, we would then get to mole ratio because we're changing our compound. So this would have been that mole to mole ratio. And by the way, this is just my quick way of showing that that's a ratio. And we use this, we find this actually in our balanced equation. Okay, so we find that in our balanced equation. And then now, finally, this would have been moles to grams. Going moles to grams, that would have been, once again, molar mass. Molar mass of NH3. All right. Is that making more sense, guys? Let me know in the chat. I'm going to continue. We don't have too much time because I do want to get through a lot more, but let me know if that made sense. And I can always do more examples in different live tutoring sessions. So that's something else we can do. So continuing on. Cool. Happy to help, Megan. I'm glad it's making some sense. All right, so our next part is saying, what is the excess reactant? So remember, the excess is what was left over, right? What was not completely, well, it's an excess. There's more of it left over. So, and this also asks us how much is left over, meaning like the amount. So what I want you to think of is going back to that smoothie analogy. And let me actually scroll back to that nice little smoothie analogy. And our excess, we said, was our strawberries, right? And we could only produce two smoothies overall. Those are our products. So 2 smoothies was what we can produce. And that, remember, is our theoretical yield. Our theoretical yield is what the limiting reactant produces. So in our case, our theoretical yield would have been the 2 smoothies. So to figure out how much is left over for our excess, we would then first start with how much we actually produced, right? So if we actually produced 2 smoothies, then that means how much did we use in the overall amount? How much did we use of that reactant or that excess reactant to make that amount of smoothies? Okay, so since everything required 1 cup, then for 2 smoothies, we required 2 cups for each, right? For the strawberries as well as the milk. So in our case, all we would do is figure out that from the 40 cups, by the way, what we initially started with, we would then subtract what we used up in the experiment or just to create the smoothie, which was 2 cups of those strawberries, and we would figure out what's left over. So then we subtract those 2, so you get your original amount, subtract it from what's actually being used up or reacted, and that'll give you your excess amount, all right? And then this would have been 38 cups. So I wish it were this easy in chemistry, but we're going to go over it. So now that we get that overall idea that we have to use our theoretical yield, what was that? The limiting reactant, what the limiting reactant produces, right? Those are definitely key topics here. And I realize I skipped one real quick. So in this case, let me go back real quick. What is the theoretical yield or amount of H3 produced? So that would have been what was it? 17.43 grams of NH3. And that was just what nitrogen produced. Okay, that's what we found. So this was our LR, or limiting reactant, and it produced 17.43 grams of NH3. That's our theoretical yield. Continuing on. So going back to this excess problem. So our step one is going to be with starting with our theoretical yield in grams that we just found. So we just found that that was 17.43 grams of NH3. All right. So if we're going to be starting with this, we're going to somehow, some way get to now grams of H2. So we're going backwards. So we're going from grams of our product to grams of our reactant. Specifically, we're going from grams of NH3 to grams of H2. All right. I'm going to develop a plan again. So our plan is going to be going from grams of NH3. And what do we notice? Completely different compounds. What do we convert to? Moles. Because once again, we need a mole-to-mole ratio to change the compounds altogether. So in this case, we would have gotten moles of NH3. Okay, then we're going to keep going. And we're going to get to moles of H2. And finally get to grams of H2. I'm going to show what I'm doing in between. So anytime we're going from grams to moles, that's going to be our molar mass. So we use our molar mass as our first conversion factor. Continuing on. Mole to mole ratio, because we're changing the compound altogether. So this would have been a mole to mole ratio found right here, right, in our balanced equation. Next, our last conversion factor would have been moles to grams, which is our molar mass. All right. So let's set it up and let's figure out how much is left over. All right, and I ran out of room. Okay. So continuing on, I'm just going to scooch this along. Actually, I'm going to scroll up. There we go. So 17.43 grams of NH3. That's what we're starting with. And we said that we're going to moles of NH3 using the molar mass. So I'm going to just put the grams of NH3 on the bottom and moles on top of NH3. All right. So using the molar mass, we found this before. It was 17.04 grams of NH3 per every 1 mole. We figured that out before. All right. Continuing on. That was just our first conversion factor using the molar mass of NH3. We cancel out the grams of NH3. We're at moles of NH3. So we'll put the moles of NH3 on the bottom and moles of H2 on top. And going back to our mole-to-mole ratio, which we find using the coefficients in front. So there are 3 moles of H2 per every 2 moles of NH3. So 3 to 2. 3 moles per every 2 moles of NH3. Canceling out these moles of NH3, we're now at moles of H2. Finally, gonna get to grams. So going to grams, I'm gonna put the moles of H2 on bottom so they can cancel, and grams of H2 on top. So in this case, H2's molar mass is 2 times 1.01, since there are 2 H2s within this question. So this would have been 2.02 per every 1 mole. Okay. Multiplying straight across and dividing, and you get 3.07 grams of H2. What did we just find? So what we just found was how much H2 was actually being used up or reacted to figure out, to actually produce our product, okay? So think of it as those are the 2 cups that we used from our strawberries to produce the 2 smoothies. Yes, kind of clicking, making sense? So that's how much we used up. I'm going to just say this is how much we used. Now to figure out how much is left over, here's an equation for you. So our total excess amount is equal to our original grams given minus the amount that's actually used. So we just figured out what our amount was used, which was 3.07. And what we started with initially was 4.21. Okay, so we'll subtract those and that'll give us our excess amount, which would have been 1.14 grams. of H2. This is our excess. That's our excess amount. Okay. Making some sense, guys. Let me know in the chat if you have any questions. I do want to get to one more thing on limiting and reactants and all this kind of concepts, and then I'll move on to molecular and empirical. So I know there's a lot of stoichiometry with this, and let me move a little bit of this so I can begin to talk about percent yields. Okay. So moving all this, now that we got our excess in and understand a little bit more on that, what that means, let me jump to the next thing. The next question is asking if 15.2 grams of NH3 is actually produced, find the percent yield. Okay, so percent yield, there's a specific formula for this. It's actual yield divided by the theoretical yield times 100. We found our theoretical yield, right? So the theoretical yield is always going to be what you're finding, what you find before. Okay, remember, theoretical yield is what your limiting reactant produces. So we really found that. We found that our theoretical yield would have been that 17.43 grams of NH3. The actual yield is typically given to you. So that's what's given to us in this question. We have 15.2 grams of NH3. This is all going to now be multiplied by 100. So this is our percent yield formula. And just because I enjoy telling horrible jokes as well as just helping you guys remember this, percent yield, it's where it's at. Percent yield is where it's at. All right. So at. Ever forget it? At. All right. So, because I used to always mix it up too. Yeah. Thanks, Megan. So that's what you can think of. Okay. Percent yield is where it's at. So AT, just a quick way to remember it. It's dorky. It's goofy. It's what I'm all about. So if we were to divide these two, let's see, this is 15.2 divided by 17.43 times 100, we end up getting a percent yield of 87%. I want to talk about really quick what in the world percent yield even is. Okay, so this percent yield is actually really good in a lab, which this is actually where you use percent yield the most. Is, let's say if you were to you're trying to make some sort of chemical reaction, right? And bear with me, I'm no artist whatsoever. So let's say we're trying to make some sort of chemical reaction, and I'm trying to pour something perfectly or dissolve something or whatnot. And if I were to spill a tiny bit of my actual reactant, right? That's an error, right? You guys have probably learned that a little bit in lab, where you have some sort of error if you spill something or if something doesn't react or there's contamination, etc. Now, your percent yield basically states that if you got like all of your product. So in a perfect world, 100% yield would mean that you did the experiment perfectly. Okay, that nothing went wrong, no contamination, no spilling, nothing, that you just aced it. Okay, that doesn't happen. We're human, right? So if you get a percent yield that is closest to 100, that's actually how a lot of professors or lab professors grade your work, is just checking your percent yield. So anything closest to 100 means that you did it right, that you didn't spill, you didn't mess it up, you know? So this 87% is actually really good. Okay. So now that we kind of get a little bit more of the concepts, I'm going to jump into empirical and molecular formulas. All right. So just understanding empirical and molecular formulas, what they are, what they mean, and I'll give you an example. So empirical formulas, it's really just a guess. So we don't necessarily know exactly what the chemical formula is, okay? So let's pretend that we didn't know what the chemical formula for water is as I take a sip of water. Okay, so let's say we didn't know. So someone just came along and said, I know that for sure there is hydrogen, and I know that there for sure is oxygen. And I'm going to just say that there's just one of each, okay? Now, that's a guess. That's an approximation. That's an empirical formula. Molecular formula is exactly what it is, okay? So we know that it's H2O. That's the exact molecular formula, okay? So empirical, just a guess. We're not sure. Molecular, the exact. Moving on. Let's say if we were to, and how am I doing on time? All right. So let's say if we were to do this actual example, I'm going to walk you through the steps. I'm going to focus on empirical formula, then I'm going to move on to molecular. Okay, so a sample of black mineral composed of iron and oxygen contains 34.97% of iron and 15.03% of oxygen. What's the empirical formula? Okay, so one thing I do want to point out, if you haven't noticed, this question isn't the best, okay? And I'll tell you why. This is always out of 100%. So there is no trick to this, really. I just wanted to show a different example, and I'll explain it a little bit more. But typically, these percentages are out of 100, just to let you know. So right off the bat, when you see these percentages, your first step, just change it to grams. There is no trick with that. Notice that I did not convert anything. I literally just, instead of putting percent, I changed it to grams. All right, so that's always step number one whenever you see these percentages. Okay, so now that we have that down, of course, we have to change this all to moles because that's what chemistry likes to do, right? They just love their moles. So in our case, we're converting grams to moles for every single element. Luckily, we only have two. So I'm going to do that, starting with the grams that we just found. I'm going to convert these grams just to moles using the molar mass. All right, so looking at your periodic table, I'll let you know how much this is. So we'll align grams on the bottom of iron, and the molar mass of iron is 55.85. All right, and then per 1 mole of iron. Okay, so that's it. We just wanted to get to moles. So these would cancel, and we would figure out how much moles specifically we have of iron. And let's do that now. This would have been 34.97 divided by 55.85, giving us roughly 0.6261 moles of iron. Okay. So continuing on, I'm going to do the same thing for oxygen. So we were given 15.03 grams of oxygen. Just converting this to moles using the molar mass, just using the molar mass, which is 16 for oxygen, dividing those two out to see how much we would get. And these steps, by the way, that I'm talking about are always the case, okay? So luckily for empirical formulas and molecular formulas, they have a nice little just systematic flow. So if you know those steps, you're really set. So this would have been 0.9393 moles of oxygen. All right, that was just our second step. So always, whenever, as I mentioned, whenever we see percentages, can just change that to grams right off the bat. After that, convert to moles. So convert your grams to moles, which we found. Next step, step 3. We then want to divide by the smallest amount of moles. So in our case, as we saw, iron has the smallest amount of moles. So that's what we're going to divide each mole value by. And I showed that here. So in our case, once we divide this, this will start to form the empirical formula, or the subscripts of our empirical formula. So the reason why I really wanted to show this question is I wanted to show you what to do when you get, let's say, 1.5 or 1.33 or just some sort of strange number that you don't know what to do. You don't know whether to round up, round down, and I wanted to go over that. So in this case, you're not getting like, and by the way, if you were to get like 0.99 after dividing this, that's okay to round up to 1. Same thing goes with like 5.98. That's fine to round up to 6. It's the ones that I'm going to mention right here that we can't necessarily round to. So this is something to definitely know. Whenever we have 0.5 or something ending in 0.5, you're going to multiply all of the numbers or subscripts by 2. Okay, so that's what we're going to do in this case. So I'm going to go back to this. So that's what we're going to do in this case, where I'm just going to multiply both of these values by 2, just because this one had a 0.5. And I'm going to show you the other ones that we have to look at. So if it ends in 0.33 or 0.66, we multiply by 3 to get a whole number. It's just to be able to get a whole number, okay? And then now the last one was anything that ends in 0.25 or 0.75, we multiply by 4, okay? Cool. Something to note. So what I did here was I multiplied by 2 just because of this 0.5. So when we do that, this would give us 2 moles of iron, really. And actually, by the way, our moles actually cancel. I should have mentioned that. Our moles cancel, and it's just a whole number. So that's just our subscript. And in this case, 1.5 times 2 gives us 3. Okay. So that would have been of oxygen. So what we would have had now is our empirical formula. So this would have been Fe2O3. That's our empirical formula. Done. Okay. Any questions so far? Is this making sense, guys? Let me know. We can move on. Making sense. Lovely. Glad to hear it, Arabella. Jessica says yes. Okay. Megan says yes. Happy. Okay. So another question. Let's do this next one. And now we are going to get to a molecular formula. So to be able to get to your molecular formula, you first have to figure out what your empirical formula is. Okay. So, and another thing, by the way, to figure out your molecular formula, you must be given the mass of the molecular formula. Okay. So there's no way around it. You have to be given that. So if they don't provide that, it's a trick. So I've seen that with multiple choice questions where they say not enough information given. If they were asking for the molecular formula and they didn't give you the molar mass of the molecular formula, it would have been not enough information. So I've seen that personally as a tutor, as well as when I was, in college getting my degree with that. So don't be fooled. Okay. So the first step, we have to find our empirical formula. And actually, the first step is to read the question. Read the question. So nicotine is composed of 74.02 grams of carbon, 8.710 grams of hydrogen, 17.27 grams of nitrogen. If the molar mass of nicotine is 162.3 grams per mole, what is the molecular formula? Okay, so figuring out molecular formula, first step, convert to grams to moles, because it already gave us everything in grams. We don't have to worry about changing percentages to grams. So we're not doing that. So in our case, we're going to be converting grams to moles. Let's so our carbon nitrogen, grams of nitrogen cancel to give us moles of nitrogen. Okay, so that's always your first step, converting grams to moles for each element that they talk about. So what's the next step? Divide by the smallest amount of moles. So our smallest amount of moles in this case would have been the 1.233 moles of nitrogen. So I'm going to do that for every single one. All right, so doing this, dividing by the smallest amount of moles, we get, and I should have canceled out the moles. Okay, so the moles actually cancel out. Sorry about that, guys. So it would have just been a coefficient, or not a coefficient, a subscript. And here we can round. So this is a nice case where we can just round. This would have been 5. Then hydrogen would have been 7. Nitrogen would have been 1. So as mentioned, since there is nothing to multiply, we can just go straight into our empirical formula. So in our case, we said that carbon has 5, and hydrogen has 7, and nitrogen only has 1. This is our empirical formula. Okay, So that was our empirical formula. But we're not done yet because we need to figure out our molecular formula. So what we need to do next is to find the molar mass of our empirical formula. Okay, so finding the molar mass of our empirical formula, there are 5 carbons, right? That's where I get this 5 times 12.01. That's just the mass of carbon. Multiply that out, we get 60.05. Now 7, we get that 7 from that subscript. So there are 7 hydrogen times our mass of hydrogen. We get this. And then now our nitrogen, there's only 1. Multiply by the mass of nitrogen. Add it all up, and we will get 81.13 grams per mole. That's the molar mass of our empirical formula. Okay, still more to go. Almost done though. And you guys know me a little bit by watching my videos. I love having tricks and tips to just remember this, and because I know there's just so much to remember. So to remember our next part, what we're going to be doing is we're going to be dividing our molecular formula mass, molar mass, by the empirical formula molar mass. Okay, so we'll divide the molecular formula's molar mass divided by the empirical formula's molar mass. So I ask you this, please, oh please, do not forget about me. Don't forget about me. Okay, so that's how you can remember it. Me. All right. So molecular over empirical, that is the main thing that we have to look at whenever we're figuring out the molecular formula overall. Okay. So hope you guys like that neat little trick that I made up. Now actually doing this, they gave us our molecular formulas molar mass, right? In the very, very beginning, they had to have given us that. So that's where I got this first number. We calculated our empirical formula's molar mass. Chris, you're welcome for the trick. Happy to help. So dividing these two, we'll just get 2. It just gives us a subscript, okay? It just gives us a whole number. So what we're going to do with this 2 now is multiply every single subscript of our empirical formula. So divided the molecular formula and the empirical formula's molar masses, okay? What we're going to do next is multiply the above results. So just multiply the subscripts of your empirical formula with that 2, with what you just found. And finally, we get our molecular formula. Okay, so this is very large. This is actually carbon. There's 10 carbon, 14 hydrogen, and 2 nitrogen. All right, so that is the molecular formula of nicotine. Okay, I also wanted to get into real quick another little trick. Before I move on to another trick, any questions here? Did this make sense? Does someone want me to go back, explain something else with molecular or empirical formulas, or is this making sense? Let me know in the chat. And then I'm going to write out my little trick, just little tidbit that I've seen before. Let's see. All right, so since I'm not seeing anyone have any questions, I'm going to move on to this little trick that I have for you that I've also seen on exams or on the AP exam, depending on what class you're in. Let's see. So let's say if I were to have, just making this up right now. Let's see. This is C6, H12O. I'm going to say 4. Sure. Okay. So let's say if you were given something like this and you were asked to find the empirical formula. Okay, so if they gave you the molecular formula and they asked you to figure out what's the empirical, all you have to do is figure out what all of these numbers are divisible by. Okay, so since all of these are even numbers, they're then divisible by 2. So we would divide by 2 to go right back down to our empirical formula. Okay, so our molecular formula is always going to be one that is going to be able to be divisible by something. Okay, we can divide by something. And then our empirical formula will not. We're not going to be able to divide by anything, really. It's just what it is. So that the numbers are typically prime, or just you can't change it anymore. So in this case, this would have been, there's 3 carbon, there's 6 hydrogen, and then there's only 2 oxygen. So that's as far as we can get. We can't keep dividing because not all of them are divisible by the same number. So this would have been our empirical. Okay, so I typically see that on like a multiple choice question. That's like a freebie right there. So like, let's say if we had, another one, and if we were to even just, think about it as, let's say, carbon, I'm going to say 3 hydrogen, 9, and oxygen. Let's say, I'm just going to be ridiculous with this and say 27. Okay. So everything is divisible by 3. So yet again, we can figure out our empirical. This would have just been 1. This would have been 3. This would have been 9. And that would have been your empirical formula. Okay. So that's another thing that I've seen on exams. So yeah, that's pretty much all I had prepared for you guys. We went through a lot of topics I know today. What I also wanted to now give you some time for, I know we don't have too much time, but does anyone have a question? Might just be able to answer a quick question before we end our tutoring session. Let me know in the chat, or actually you could even ask a question on the below button. You can literally press that, ask the question, and I will answer it. Let me know if you guys have any questions, as well as make sure to save your spot for next week. If you're just joining us, if you join later on during the session, reserve your spot. At the moment, I am not too sure what I want to cover just yet. That's why people have been writing what they possibly want me to go over. I've seen net ionic, I've seen electron configuration, and this is just me to see what I should be going over overall. So if you have any other anything else that you actually suggestions overall that you want me to go over for the next Sunday, let me know in the chat. I really, really want to know your feedback, just because I want to be able to also, release videos for you guys too. I'm working on a bunch of really cool things for you guys. So yeah, if there's no other questions in the chat, Megan actually just said something. Let's see. Jessica, oh, thank you. So first, Megan said, I don't know about everyone else, but stoichiometry is still a little over my head. Okay, thank you so much, Megan. That helps me. I definitely want to go over that more, because it's really important to know, just because it is a big, foundation of chemistry. So thank you for letting me know. That just helps me know what to teach for next time. Jessica says, nice tricks. Thank you. This is helpful. Thank you. I feel more confident for my chemistry class. Beautiful. I'm so happy to hear, Jessica. That's seriously awesome. That's exactly what I want you guys to feel, is just confident. Diana says, thank you so much. Happy to help, guys. Really. Oh gosh, I'm so happy to help you guys just feel more confident in, in yourselves and your chemistry classes. It's a big thing with education. I know, if you don't get it, so I've been there. So Megan also says, yes, thank you. Yeah. Happy to help. So at any point, if you have any more things that you want me to cover, whether it be I'm getting stoichiometry, I'm getting all these other things that just great ideas, let me know if that comes up. Also, as I mentioned, reserve your spot now, as well as if at any point, you want to rewatch the replay, it is going to be up. So if you want to relook at these questions, maybe, spend some time looking at this over and over and practicing the same questions, I do recommend that. I agree. Yeah, stoichiometry is difficult. Melissa, I'm so grateful for, thank you. Thank you. That's so kind of you. I'm so grateful for you guys, really. Thank you for being here on a Sunday and just wanting to do chemistry with me. So I'm happy to have you guys. Thank you once again. And I will see you next Sunday. All right. So have a beautiful night, guys. That's night for me, but I'll see you guys later and see you next Sunday.